So welcome for the last session for today, which is reconstruction calibration based on objects in your data. So Andrew has already shown you you can use the crystallography in the data, if there is crystallography. But more often than not, we actually have certain objects in our data that we can use for reconstruction. And we might have knowledge about these objects because we might have correlative data. We might have electron images, transmission electron microscopy images. You might have images from scanning electron microscopy. Or you might work with objects that are extremely regular. If you're, for example, working with microelectronic transistors in microelectronics, it might very well be that you have a lot of knowledge about what this transistor should actually look like. Some idea about shapes and so on and so forth. And so the question is, how can we make use of those shapes in order to work with our reconstruction, to drive our reconstruction? Unfortunately, in an hour and a half, I don't think we're going to get far enough to go into depth into how to drive a reconstruction using that. There is some stuff in one of my older papers, how to write a solver that can do stuff like that. But we're definitely going to get into how to reconstruct objects and how to unreconstruct them, and how to essentially create a feedback loop that you can use to optimize your reconstruction. Okay, so the question is, where do we start now? Well, the first thing I'm gonna show you is actually what do we mean by objects and how do we represent them, and then we look into what can we do to reconstruct them. You already seen an example earlier today. The dataset hull, that's always a very, very important object for us. But then I'm just loading the dataset that you got for isosurface delineation. I think I'm just gonna use the isosurfaces, because that's a very good example of something you can use, because your isosurfaces represent precipitates that are in a superalloy, for example. That's the dataset that we're having here. They're usually either cubes or they're round. So you can say, okay, maybe I can fit in each of those objects, maybe I can fit a sphere and then drive the reconstruction until the sphere is matched as well as possible. And I think this is just a good example to use. Tomorrow we are going to use we're going to start modeling stuff. So we're going to use Blender a lot. But today, I think in an hour and a half, we're not going to have enough time to do modeling as well. So okay, so let's get started with while the image transform is running. This is obviously also a reflection data set. So I'll just have the inference the transformation run in the background. And if you go into it's the teaching material, if you go into test data, there's a data set that you have that's data for isosurface, and that's the one I'm currently using. And for that one, lo and behold, what did it? That's weird. For that one, for example, well, we have an image. Image is always helpful. Could probably be a better image, but we have an image. It's better than nothing, right? So I have a bit of an idea of what the sample could look like. It would even be better if we had a transmission electron microscopy image, ideally one where we know which angle we're looking at it. So if you put it into your atom probe and you have a TM image, it would be nice to know from what projection that is. So if you do that kind of work, always make sure that you have some rotation calibration between the sample in your transmission electron microscope, scanning electron microscope, whatever, and your atom probe. Yeah, and in this case, using just the copper crimp tubes is usually not all that great an idea, because you're definitely gonna lose that orientation relationship. Yeah, so you're gonna have to use something else. I mean, one very easy thing you can do is just squish your copper tube so that you always know what direction you're looking at. Yeah? But you have to really make sure that you know that. Okay, so the question is now, what are objects? What are objects, and what do we mean by objects? And essentially, if we have our APT data, what we have is we have an atom, and that atom has an x, a y, a z coordinate. It has an x detector, it has a y detector, it has some kind of identity, be it mass to charge or identity, maybe you have identified what isotope it is, and so on and so forth, and so on and so forth. So this is essentially our APT data, and we also have APT objects. Yeah. And our objects can be 0D, they can be 1D, they can be 2D, and they can be 3D. Yeah? And these objects are actually usually piecewise linear approximations. Yeah? Piecewise linear approximations of the real object. And you've probably come across one of them already, an isosurface. That's, for example, a 2D object. Yeah? It's a 2D manifold in 3D, so that the object, all of our objects are actually in 3D space. But their mathematical dimensionality might be anything up to 3D. Yeah? So 0D might be a cluster location. Yeah? Maybe a cluster location. It can be a work coordinate system origin. Yeah, it might be whatever. Yeah, and it's represented by a point, and that point has an x, a y, and a z coordinate, and potentially an exit at the. Maybe we'll just write it as vectors. Then it's. I shouldn't have written that much. So it has a. It has a vector in reconstruction space, and it has a vector in detector space, and we'll get into how we get into the detector space. And the same for here, right? We have an x and y, the c x detector, y detector, and the one thing I was missing in here is actually the evaporation number sequence. Yeah, I don't know what we call it. Evaporation index. Yeah, very often in our atom probe data we actually treat that as implicit, but that's not a particularly good idea. So if you look into our code, you will always see that in our POS files, in our POS variables, we've always explicitly have an extra line for ion index, so that if you take a sub volume out of this, you still know which ion index was what. So we've got this ion index, and these are actually the detector X, detector Y, and the ion index. Let me show you so detector X, detector Y, and the ion index. That's the coordinate of your atom in detector space, and X, Y, and Z is the coordinate of your atom in reconstruction space. Then we have one-dimensional. This could be a dislocation, for example, or it could be I don't know, whatever. Can you think of any other line defects? Sorry, off the top of my head. Maybe I've been in dislocation land for too long. Could be a triple line. Whatever line object you have, and this one actually consists of points and lines. So you have points, you have vertices, we call them vertices. So you have vertices, and we have lines. And so it consists of a list of vertices, each of which all has an X in reconstruction space and an X in detector space. And so, the detector space is detector X, detector Y, hit sequence number. Yeah, and then each one of those also has an index. Yeah, and each line element here connects to indices. It's a list of index 1 and index 2. Yeah, and obviously this is repeating, and here this is repeating as well. And from that we can build up a piecewise linear approximation of that object. Then we have 2D objects, and that's usually what interests us the most. Yeah, what interests us the most, and the 2D object is then, for example, an interface, surface, whatever. I'll just need more space to draw now. That's why I'm not gonna write a couple of examples. And here, this is going to be made out of triangles, triangles. And so the thought is exactly same as up here. Yeah. So what we are going to have is we're going to have vertices. Yeah? So these here are vertices V. These here are our line elements L. Yeah? And here we've got our vertices V that also have coordinates in reconstruction space, coordinates in detector space. Yeah? We have line elements L, and we have triangles T, or we call them faces, and you'll see in a second why. And the faces then consist of index 1, index 2, and index 3. And usually we only list the faces. We don't list the lines, because we can get from the faces to the lines just by simply permutating the individual indices here. And finally, we have 3D objects. They're obviously volumes. Yeah? And usually, very often in Atom Probe, we're actually using rectilinear volumes. But what we are going to do here later is we are going to use tetrahedral volumes. Yeah? Because a tetrahedron is the simplest possible geometric object in three-dimensional space. Yeah? It's the so-called 3 simplex. You can have simplices in n dimensions, and you can already see in a 0-dimensional space the point is the simplex. In a 1-dimensional space our line elements are the simplices. In 2-dimensional space the triangles, and in 3-dimensional space the tetrahedra. Same story here. We have vertices, we have edges. Yeah? We have edges, lines or edges. We have triangles or faces, and we have volumes or tetrahedra. And we are going to make use of the tetrahedra later on as well. And the same story here. I can write the tetrahedra, and the tetrahedra is going to have index 1, index 2, index 3, and index 4. I can do the same thing as before. I can permutate those 4 indices to get to the faces, permutate the faces to get to the lines. So usually we will just list the tetrahedra, because if we want to, we can get from the tetrahedra to the lower dimensional simplices very, very easily. Yeah, this all sounds very theoretical, but if you are a computer gamer, if you like any kind of computer graphics, you might already be very familiar with that. Yeah, so if you buy the latest gaming console, they're always showing off how many triangles per second can this gaming console handle, because the finer the triangles, the more realistic everything looks. And one of the programs these game assets are made with is Blender, and this is what we are going to use quite a lot today and tomorrow. And now here I've got a 3D scene, so you can see in those 3D programs you've got a 3D scene. You should already be familiar with that. And I'm just going to delete all of the objects in there and just add a random object, just add a monkey. And you see that monkey is, if I go into edit mode, is made from individual, quadrilaterals, not triangles. So why is it quadrilaterals? Well, very often Cartesian quadrilaterals are just giving us nicer meshes, but they have one downside. I showed you just before that the triangle is the simplex in the 2-dimensional world. So why go to quadrilaterals? Well, because you get simpler topologies, and mesh topology is something we're going to talk about a lot tomorrow. But it has one downside, and that is 4 vertices are not necessarily in one plane. And for us, this means that I have 2 ways that I can split up one of those quadrilaterals, which will give me 2 different surfaces if they're not in one plane. And that's why we are going to avoid them. We are going to avoid them, at least for the most part, and we are just going to be using triangles. But yeah, let's go back to maybe I'll just bring our Suzanne back. We're going to edit mode. I can click on each of those individual vertices, and I can select them. Tomorrow you'll see we can even pull our atom prop data in and do the same thing. And I can just look up, okay, where the vertex is. And the same thing, I can choose, I can select faces, so I can go from vertex select mode into face select mode, edge select mode, or face select mode, and then I can, for example, select one individual face. All right, so, and we are going to be able to edit that and work with that and so on and so forth, but that's not as important for now. Okay, so back to the whole reconstruction business. And I will just switch off, I will just get rid of the curve fitting tool. No, not save the curve fitting session. I'm going to get rid of all of the other stuff that we had and gonna jump back into here. And I will just load the ranges for the data set that I'm working with right now, which is the where do you go? No. Test data, data for Isosurface, range fig, open. So we've got our ranges for said data set, and I will just rerun the allocation because that was obviously something I couldn't really run before. Okay, so we've allocated the ranges, and allocated the ranges. We've done all of that funky stuff. Oh, I could have just run the whole thing. And I'm just rerunning the ion volume calculation. Okay, that's all done. Then we are creating a detector hull. Will take a couple of seconds. So whenever we do algorithms that take a little while, so one of you can start telling us something interesting. Tell a story out of your life. Okay, so we've got our detector hull calculated, so that's all good. We can set up our reconstruction. And right now it doesn't actually matter all that much if it's a good reconstruction or a bad reconstruction. We'll just set up a reconstruction. Calculate the radius, this time just in a very simple way. Run our reconstruction, and I hope aluminium makes sense in that data set. Yeah. And here we've got our reconstructed data set. Here we've got our reconstructed data set. And in this reconstructed data set, we've got our aluminium, and I will just plot the aluminium maybe separately as well. And maybe we're just gonna plot 100,000 atoms. No, that's 10,000, 100,000 atoms. Is that too much? Probably is. Anyway, it's a nice superalloy sample. You can see we've got some nice precipitates in there. Yeah, so this is actually pretty cool for our purposes. But what we don't necessarily know is whether they actually look the way they should look. Yeah, and maybe we can just work on on making them look the way they should look. Okay, so I'll just copy that. Into the chat. Okay, so we've got the first reconstruction, and now what I'm going to do, I'm actually going to export this this hull that we have into Blender. I've showed it already before a little bit how to do that. So we're just gonna go patch to OBJ, and we're gonna do that with the reconstructed hull. So I call that hull R, I think was it hull R? Let's go back. That's why we have all the code. Yeah, hull R. And so we're gonna export that. And hull R is actually not just a single object. It's an array of patches. So if you look here, you've got 3 patches in there. So you've got 3 objects in there. And each of those objects is a list of those vertices that I've just explained. It's a list of those vertices and a list of faces. And this is just the indices. You know, that triangle number 68, it goes between vertex 34, 66, and 65. And that's all there is. That's all there is to those objects. And now we can go into Blender and go File, Import, Wavefront OBJ. Sorry, I did that with shortcuts. Maybe that's not as instructive. So File, Import, Wavefront OBJ. Yeah, because that's actually a very readable data format, and I'll just show it to you so that you can see it for yourself. So this. Oh, I haven't actually exported it yet. So we can just open that with the text editor. The text editor, and what you can see is that it's just a list of those vertices as a text file, and then at some point the vertices end, and we have an object mesh defined on those vertices, and here you see the individual triangles. The first phase starts at vertex 5001. I don't know why it doesn't. Yeah. Anyway. Yeah, and this is how defined that. So the speciality about those Wavefront OBJ files is that they're very, very old files from the 90s, but they're still very popular. Sort of the smallest common denominator for a lot of computer graphics, so you can load that into any 3D printing software, for example, and so on and so forth. Yeah. Anyway, this is just a list of those vertices and the faces, and the objects. So the vertices are defined for all objects. whereas the faces make then individual objects. Yeah, so all the vertices are shared between all the objects, and the faces are not. In our case, of course, none of the vertices are actually shared between the objects. Yeah? But each object has its own vertices, but in the file it's that way. So when we load them in, we just need to make sure that the orientations are the same as we intend them to be. And we want Y to be forward and Z to be up. Yeah? For some reason in the 90s, computer graphics people used -Z forward for whatever reason. I don't know. Yeah, that's just the way it is. So we just need to make sure that Y is forward and Z is up. Of course, if you stay consistent with your coordinate systems, you can just stick with the defaults. You just have to stay consistent then, yeah, and I guarantee for nothing. Yeah, but go Y forward and Z up, because then the coordinate system in Blender would be the same as the coordinate system in MATLAB that we're using. Okay, and we can go to downloads, and I think we haven't written it out, have we? No, we haven't, so we still need to write it out. So patch to OBJ with our hull, and I'll save it in the downloads folder, or maybe I should save it where the data is. Probably be a good idea. APT school data, no, test data, data for Isosurface, and it's hull R. Usually I would use the name of the data set, but yeah. Everything is a bit more complicated in Windows. Sorry to have to say that. Anyway, so now if I go and crap, now I have to navigate there here. Oh, bloody hell. Education, no, not education. Events organization, conferences, APT Winterschool, APT, no, test data, data for Isosurface, hull reconstructed, Y forward Z up, import OBJ, and ta-da, we've got our OBJ here. And I hope you all know how to navigate in Blender. For everyone that's maybe a little behind on that one, middle mouse button for rotation, shift middle mouse pen for panning, and the scroll wheel for zooming. And now we can actually, so I'll just make the whole thing a little bit transparent. So I'll just select it by clicking on it. And if I go into Object, Viewport Display, I can just show, say show all edges and show the wireframe and display as wire. So in this case, of course, we've got three objects that we loaded in with that file. The top cap and the bottom cap. We're not going to care about that too much right now. And we have the outer mantle. And we're going to need that a lot for modeling of grain boundaries and the like tomorrow. And one thing I can do now is I can just create an object. I can just create any object I want. And maybe we'll just start with something simple. And that simple thing is going to be a plane. That's the simplest thing I can think of. So we go mesh and create a plane with Shift A, mesh plane, and then we'll just move it somewhere in the middle of the data set. So we'll just grab it in the Z direction, and it says meters, but anyway it's nanometers, you all know that, and I'll put it at 150 nanometers in the Z direction, and by pressing S I can scale it up, and I will scale it up to be what, 25, 30, doesn't really matter. So put a scale of 20 onto it. So now it's 40 nanometers across. And it just lives in there, and it's just a plane in our reconstruction. And that plane could, symbolize all kinds of things. It could symbolize a grain boundary that's there. It could, or it could outline, I don't know. It's a plane. Okay, so next thing I'm going to do, is to select the plane. Okay, did I go into to select the plane and go into edit mode? And you do that with the tab key. The reason why I'm doing it is because the plane only consists of 4 vertices right now, and we're not going to see much if we do an inverse reconstruction there. So I'm going to go and subdivide it. Is there a new key for that? It should be W, should be subdividing. Bloody hell. Anyway, it's been maybe I should have chosen a different. Maybe I should have chosen. It used to be W. Why is W no longer subdivide? That is weird. Does anyone know what subdivide is now in Blender? Mesh. Face, it would be under faces probably. Extrude, insert, intersect, world shade, no face data. No. Extrude, insert, wireframe, fill, beautiful. But we are in edit mode. We are in edit mode. Yeah. Oh. Did we select the face? Selected the face? Face. That is extremely annoying. Subdivide, it's under edge. No. Okay, so now we're going to subdivide it, this plane, and we're going to subdivide it into, I don't know, 10 divisions, 9 divisions, 9 divisions, yeah, some divisions. So now we have a plane that's outlined by quite a lot of vertices. Yeah? So it's now 9 subdivisions, which means 10 vertices on each side. Which means if I click on one of those edges, then you'll see the edge is then 2 meters long, or 2 nanometers long. Okay, and now I'm going to go and export this edge. Yeah? So I'm going to go File, Export, Wavefront OBJ. We're going to use OBJs again. And I don't know, what are we going to call this thing? Oh, I have to navigate to the... Oh, bloody hell. That is a lot easier on a Mac. Sorry to have to say that. Anyway, so public, events organization, conferences, APT Winterschool. Maybe I'm also too stupid for Windows, who knows. Test data, data for Isosurface, and we're just going to call that demo plane. Yeah. Demo plane. And here we unfortunately again have to make sure Y forward and Z up, so that we stay inconsistent. And we're also going to triangulate the faces, so all the quads I've created now, they will pop up as triangles in MATLAB later. And we don't have any materials. Materials would mean that we have some colors and stuff. We don't have any of that. And we haven't applied any modifiers, so that wouldn't do anything anyway. And we will just export that. And if I go into the, here, you can see the demo plane thing is here now. And I could just open it with the editor. And obviously this is a relatively short file, and you'll have, you have a bunch of faces defined here. And you can see they're all triangular faces, which is all good. And we have a lot of objects because I forgot to also say that we only want to export the object that I've selected. Yeah? So File, Export Wavefront, OBJ, demo plane, and we're still at the same directory as before, and we only want to limit it to selection. That was my bad. And now if I open that with the editor, it turned out I had nothing selected, so this was a relatively short file. So again, file, export wavefront, export wavefront OBJ, demo plane. Now we have something selected, and let's open that with the editor. And now we can see it's a much shorter file, and with essentially only that plane defined. And we have, for that plane, we now have the vertices in reconstruction space. But what we really would like to know is, now we've defined in our reconstruction object, how do we get into a detector space? And this is where the volume objects that I was talking about earlier, where these come into play. So what we're actually doing, and you're going to see that a couple of times more tomorrow, is something called the Barycentric Transformation. So we need to have some way. To get from our, detector stack, which has X detector, Y detector, and N. You need to have some way to move between this one and our atom probe reconstruction. Our atom probe reconstruction, which has X, Y, and Z in natural coordinates. And this is our atom probe recon, our atom probe reconstruction, but we also need to have an inverse of the reconstruction. So our reconstruction, and we need to have our recon to the power of -1. So how do we do that? And the way we do that is actually because by using an approximation. That approximation is by using the coordinates that we know about. So the coordinates we know about are the atomic coordinates. We know the atomic coordinates both in detector space and in reconstruction space. So what we can do is actually take the coordinates that we only know in reconstruction space, which are object coordinates, and interpolate between the coordinates in the detector space. And the way we do that is, the way we base it on is that neighborhood relationships are not broken. So just imagine I'm taking these 6 coordinates here, which would be in detector space maybe here, and I'll create one of those triangular meshes, between them. And topologically, I did that wrong. I can have the same mesh by using the same faces and vertices. This should actually sit a bit further out here. Same vertices between here and here. So if I have a coordinate that I only know is somewhere here, I could go and look up where it is here. And that's actually the same trick you've probably heard of people having on Instagram, having their photos photoshopped. It's actually the same transformation that we're using here. It's called a barycentric transformation or barycentric coordinates. So if I just take that the triangle over here and blow that up so that it's easier to see, then I can say that my point that I'm interested in is lying here, relative to the coordinates of the corner vertices. And our corner vertices in our case are atomic coordinates, coordinates of individual atoms that we've measured. And we connect that with the triangle here, which, in this case, this one has an x1, x2, x3 coordinates, x, y, I was stupid. it has an x1 because this is our vertex 1 and y1 and a z1. That one has an x2, a y2 and a z2. And that one has an x3, y3, z3. And here we've got a triangle with the same triangle, just in recon space. So this is in recon space, and this is in detector space. And here this corner has an x. Let's start at the same one. So this is has xd1, yd1, and n1. N being the evaporation sequence number, and here we've got an xd2, yd2, and an n2. And sorry for writing over other stuff. And here we've got an xd3, yd3, and an n3. And so how do I get the coordinates across here? Well, by using barycentric coordinates. And barycentric coordinates means essentially you give a weight to each of those vertices, so that if this was, if you would hold a triangle and the triangle itself doesn't have any mass, and you would put weights at the corner of each triangle, so that the point that you're holding it, would be the center of gravity, the barycenter, center of gravity. And so in this case, of course, the boundary condition is for barycentric coordinates. The nets is that, if you have a triangle and your point is here, so the barycentric coordinate of this point here would be, it's a 3 in 2 dimensions. It's one redundant coordinate. So in this case, it would be, if this is index 1, index 2, index 3, the mass would be 1, 0, 0. If we looked at a point right bang here in the middle, it would be 1/3, 1/3, 1/3. So essentially the sum of all 3 coordinates is always 1. So the sum is 1. The sum of those 3 barycentric coordinates is always 1. Of course, you can also do that with a tetrahedron. You can just imagine you put weights on each corner of the tetrahedron so that it's well balanced around whatever point you're looking at. And a good thing about that is that this allows us to interpolate or transfer this coordinate point from detector space into reconstruction space. And with this, we have actually an approximation for our inverse reconstruction. All we need to do is build up a tetrahedral mesh for our reconstruction in order to be able to do that. How do we build up the tetrahedral mesh? That's actually relatively simple. You just take your atomic coordinates, either all of them, if you have a computer with a huge amount of memory, or you take a sample of them. Take a sample of them because you don't need to know all of the individual atomic coordinates. It's fine if you just know a subset of them, so long as the individual triangles are small enough for the linear approximation, so that the piecewise linear approximation that we have to work. So there was a lot of explanation for actually very little for you to do, because all you need to do is you actually need to load the object into MATLAB, and that's relatively easy. So we have got a function called I'll just call the variable I loaded into OBJ, and we have a function.
You're not on the MATLAB screen.
Oh, thank you. Thank you for the hint. OBJ equals OBJ to patch. So we'll load that in. And if you don't pass a file name, it will just pop up with a search box, and then we can. I don't know why it never goes to the right folder. Anyway, I stopped caring. Data for Isosurface, and we'll just take the demo plane and open the demo plane, and we'll have a new variable called obj. Let me just open that, and maybe I'll just close some of the other variables. It's getting ridiculous over here. A lot of them don't exist anymore anyway. And here we've got a list of vertices and objects. In MATLAB, we actually usually have one object as one variable. So there's a bit of a discrepancy between the file and the way we use it in MATLAB or Python or whatever. And here we only have one object. So you can just go into the object and you find the faces here. But you might have more than one object defined. That's why we can't just go and have a one-to-one correspondence. So we'll just create a patch object, a so-called patch object, and we'll call that FV for faces and vertices. That's how people doing MATLAB very often do that. And we'll define that as a struct. So we'll just go fv.vertices equals obj.vertices and fv.faces equals obj.objects.faces. In this case, it's only one object. If there would be more than one object, you will have to tell it which object. But in our case, so it would have to be object 1 or 2 or whatever. In this case, with only one. And this should give us a patch object that we have here now with faces and vertices, and that's what we are going to be working with. Well, I'm going to plot that in the reconstruction. I'm going to plot that in the reconstruction in a separate page now. So I'll open a figure, and I'll just do the plotting of the. I'll just copy and paste that from here, so it's a little bit easier. So we'll just put in the I'm gonna make the I'm only going to plot the I'm not gonna plot the faces of the I'm gonna make completely transparent faces so that we can see what's happening inside. So we already have that here. So, and we're gonna make it a nice atom proby appearance. We've got a command for that. It's called APT phi axis. It's called axis spatial APT phi. Sorry, used to be called the other way around. If you run that command, it will just make your current axis be atom proby, which means you get coloring. So red for X, green for Y, blue for Z, just like usual in 3D world, and X is equal and an inverted Z coordinate, just like we do it in atom probe usually. And then I'm going to plot the object that we have. So I'm going to go patch some other. I'll give it some other color, and in this case, maybe we'll make it a little bit less transparent. And let me just give you all of that code. And now, if we look at our 3D view, you can see we've got our plane here, just like we defined it over here in Blender, and that's all good. That's what we want. But the really interesting bit comes about now, because now I will just run a 3D deconstruction. The inverse reconstruction I've called deconstruction. I don't know if that name makes sense, probably not. And in this case, as I've just mentioned before, we're building up this tetrahedra by using a sample from our POS file. Yeah, so 10 to the 5 atoms works quite fine. You can use so 100,000 atoms. You can use 1,000,000 atoms. Yeah. If you have a supercomputer, you can use all of the atoms. So I've got a MacBook Pro in order now with 64 gigabytes of RAM. So I'm going to use all of the atoms in future. But on my current computer, that's not really an option. Maybe on this one, this is a pretty good workstation. Maybe on this one, we could do that. Anyway, usually about 1,000,000 atoms works quite fine on a 16 gigabyte RAM machine. And it's good enough for the reconstruction. Yep. So it's now doing that Delaunay. So essentially building up that tetrahedra. That's a Delaunay that's the Delaunay triangulation that we're doing. And now what we have here is essentially, oops, why is it not rotating? I want it to rotate. Come on, rotate. Go home and axis square. Okay. I'll just switch the rotating on and just rerun everything. I know it's a bit inefficient to rerun the entire algorithm just because I want the rotation switched on. Anyway, so what you can see in here now, and let me just pop that out so that you can see it a little bit clearer. I'll open it in a separate window. So what you can see now is that now we have a plane now in detector space. The same plane that we had before, we now have in detector space. We now have in detector space. And you can see we have some distortions on the side, because this is just the way it's moving inwards, and it's a little bit bent upwards. But essentially, if I now go and throw that plane into the reconstruction again as a co-reconstructed object, what's going to happen? Obviously, it's supposed to come out exactly the same way as it looked before, which means we have completed the cycle. So let's go and do that. And I think we're gonna do that here in the reconstruction. So what I'm going to do here now is actually do the reconstruction separately here. So I'm just gonna call that then object reconstructed, or what did we call it? OBJ. So it's OBJ reconstructed, and we're not co-reconstructed the detector hull anymore. We could do both. We could throw everything in. Or maybe we'll just do that. So we'll call that object reconstructed. And we are going to use the detector, and we're going to add to this array. So this is an array of patches. We're going to add our, what was it called? Our deconstructed thing. FV detector. Okay, it's called FV detector. So it's FV detector. And now is that a hull detector 1 2 3. Well, that should be fine. Why are you complaining? Hull detector, FV detector. Hull detector, FV detector. 1 2 3. Okay, I honestly to God I have no idea what I did wrong, so we'll just use our FV detector. Then should be FV detector. What in the world? Oh, I know what the problem is. Because it goes over 2 lines, I only executed one of the lines. That's obviously a bad idea. Sorry, it's been a long day. So we'll just copy that again in. Maybe I should use shorter variable names. Anyway, so we're gonna go use obj objects reconstructed, and we're gonna use in this case FV detector, and now it's doing the reconstruction. And now if we plot our plane, then it should perfectly be where the plane originally was. So I'll just open a new figure. And in this figure, sorry, I'll just leave it off screen for a little bit so it's easier for me to click on later. We're gonna go and put in our patch FV. That's the object that we originally loaded in. And on top of that, we're going to plot our obj or reconstructed object. And lo and behold, I should have not used the same color. That was stupid. So I'm just gonna delete both of them and plot the first one again and the second one and give that one a different color, ideally a completely different color. And we are going to APT-ify our axes. And you can see that they are perfectly on top of each other. So what that means is that we have successfully completed an entire cycle of reconstruction and deconstruction. So we can now do that with any object that we like. And the first thing we're going to like to do is to do that with an isosurface. I think this is going to be very much fun. Okay, let me just copy all of that into the... let me just copy all of that into the chat. And now I'm really bugged by not being able to... combine the two. So we wanted to have the hull in reconstruction space. Now the hull in detector space. The hull in detector space. And that should actually be able to be combined with what was it called? FV detector. FV detector. And now it's happy. Okay, so the question was, is it an array that goes in this direction? Is it a column array or is it a row array? And apparently I've created it as a row array. And now you could actually go and reconstruct all those 4. Why not do it? Why talk about it? Why not do it? So we can go and use our objects, and I should have called them object detector. But we're gonna delete all of that and work with other objects later anyway. Do a reconstruction, and then it does all of the objects. And you can have as many objects as you like. You can have as many objects as you like. You can have a whole bunch of isosurfaces and whatnot. Any amount of objects you like. And since object vertices, your objects might only have a couple of 100 vertices at the most, it's not actually going to change much how fast the reconstruction goes. So how many atoms are we actually reconstructing? How long is that POS file? This is about 21 million atoms. Let me check how long that takes. Tick. So tick and tock are the ways to measure timing in MATLAB. I don't know if it's super cool, but Yeah, so it takes about a second or so to reconstruct those 20 million atoms. It doesn't take very long. By the way, this is on the CPU. On this computer, you could also go onto the GPU, and then it would be a couple of milliseconds, and then it goes very, very, very fast. Okay, so let's create the isosurface then. The isosurface, we have a workflow for that, by the way. Where is the isosurface workflow? There's the isosurface workflow. So the first step in the isosurface workflow is just to create the bins. That's actually part of another video, so I'm not going to go into detail about how to do that. Then we are going to create an isosurface, in this case from aluminium, I guess. Just calculating the voxelization. And this is a 1.5 nanometer voxelization. I don't know if that's a good idea or not. I don't know, but you can change it to whatever you want. And now we have a concentration variable. So you can see here, we've got concentrations here. I can actually go and open, there's a volume explorer here usually. Where's the volume explorer? Because MATLAB finally has volumetric imaging. Dicom browser, volume viewer. Oh, and there's a new volume segmenter. So I guess you can do isosurfaces directly in the volume segmenter. Let's try that out. I've never tried that. Would be fun. Anyway, so you can import a volume from the workspace. In our case, we're going to import concentration. And then you can already see, maybe that wasn't the stupidest choice. Can play with the opacity a little bit. So maybe that wasn't the stupidest choice. So we already see our individual voxels here. So that's all good. But knowing that they should be kind of roundish, yeah, they don't look particularly roundish. Maybe not as bad as I would like them to be right now. Maybe I should have taken some worse reconstruction parameters. Anyway, we can always make stuff worse. That's always possible. So let's look at the volume segmenter. I actually haven't looked at that one. Maybe that can do some funky stuff that really makes it fun for us. Okay, so whatever that thing does, it does not create isosurfaces. Okay, doesn't matter all that much anyway. So the next thing I'm going to do is I'm going to try and get a good estimate of what a reasonable ISO value would be. Do we have that in here? Now here we already jump in with the ISO value. By the way, we also have an isosurface widget app that does a couple of funky things that lets you choose stuff. But now we'll just stick with the isosurface calculation as it is here, and we can just go and create a new figure where we plot a histogram of all of the concentration values, such just that we can see where we can set up where we would have a reasonable cutoff. And so we can go histogram and concentration. And now, very important, just one colon. And the reason for that is that we don't want a histogram on all 3 dimensions. We just want a histogram of the individual values. And in this way, MATLAB just treats it as one vector. And we want, I don't know, 100 entries or something like that. And now if we look at that histogram, we can see we have some extra values here. So probably about here is a good cutoff. Yeah, so you can see this is the aluminum content in the matrix, and this is roughly the aluminum content in the precipitates. So round about here would probably be a good value. So that's what, 7%, 7-8%. Yeah. So I'll probably do, I don't know, 7%. Let's try 7% and see if it looks reasonable. So our ISO value in atomic percent. Oh, okay. Martina already calculated in atomic percent. So it's 7. 0.07 in concentration is 7%. And we give it a nice color, and then it will be plotted. So this is our isosurface. It's not particularly clean. We're going to talk a lot more about cleaning up isosurfaces tomorrow when we use them for analysis. It doesn't really matter all that much. Maybe we'll just move it to a higher value. Maybe we'll just move it to 12% or whatever. Doesn't matter all that much. Yeah. But now, and I shouldn't have called the other variable FV, because now we don't need the plane anymore. Anyway, we've written over our variable before that was called FV. Yeah. Now we've got the isosurface. Yeah. And I can actually do the same thing as I did before. So FV, now our variable FV is now our isosurface. Yeah. Is now our isosurface. Where is it? It is here. You can see it's a much larger file now. Maybe 1.5 nanometers was a pretty fine. Let's just rerun everything with a wider voxel size. So let's rerun everything with 3 nanometer voxels. This will give us a much less noisy, noisier isosurface. With a lot fewer vertices. Maybe 3 nanometers on this extremely large data set, maybe 3 nanometers is still a bit large, yeah? So let's rerun it with 5 nanometer voxels. That's a pretty big voxel size. By the way, if any one of you is tempted to ask what an optimum voxel size is, there isn't one. Yeah? A voxelization is a histogram, and histograms have no optimum binning. This is not something that exists. Yeah? This is mathematically not a thing. Okay, so we'll rerun the voxelization, and we'll rerun the isosurface. Yeah. And now we have a much wider isosurface. Okay. So now you can see we've got the isosurface, 12% isosurface, which kind of outlines our objects pretty okay. Now tomorrow we're going to get into how to manually outline objects, because objects that are not topologically spheres, you don't get topology for free. So you have to create the topology yourself. If you come up with an algorithm that creates a topology for you, leave atom probe tomography and sell it to Microsoft or Apple for millions and millions and millions of dollars. Yeah. So unfortunately that's not a thing, yeah, and we'll have to create the topology by hand. And we've created a lot of internal vertices, so maybe that was already a bit of a high value. Maybe we'll need to go to a little bit of a lower value. Now that was, I think 7% was something that we had before, because obviously already in the precipitates the value was a little bit low. So let's have a look at that again. Yeah, so essentially we've created isosurfaces inside the precipitates, which is definitely not something we want to do. Maybe we'll just need more than one species. What else would be in there? If it's a superalloy, it would be nickel as well. NaAl. Yeah. Nickel, aluminium. would probably give us a little bit better statistics. And the ISO value is probably going to need to be a little bit higher. Now we can rerun the whole histogram again. Oh no. Oh yeah, I guess that's some good separation between matrix. Yeah, so the matrix is probably here, and this is probably the precipitates, and that's some pretty good separation at a value of aluminium plus nickel of 0.6 roughly, or 60%. Okay, so now 60% is our threshold, because of course there's a lot of nickel and nickel-based alloy. Now I hope all of those surfaces come out a little bit cleaner than before. Well, a little bit, but anyway, we're going to talk more about isosurfaces tomorrow. The important bit is now we have those isosurfaces and we can use them for reconstruction calibration. So the question you might ask is, why don't I just look at the atoms themselves and use that? Well, it's going to be very difficult to correlate the atoms themselves with any images you have, yeah? With the isosurface, for example, or with the density, even the concentration profile, you can just create a projection of that into any plane you like, and say, okay, match that with an image, for example. And with individual atoms, that's going to be a little bit difficult. And of course, you're going to have certain shapes driving your reconstruction. The simplest one we're going to look at tomorrow is just having a grain boundary. If you just have a grain boundary, you can just say, okay, maybe we'll want that to be flat. If I know it's flat, maybe it's bound, maybe it's curved, maybe I know what the curvature is. Could be any information I have. Okay, so now we can go back into our reconstruction script, and since we've already called it FV, we can go into the inverse reconstruction without having to change anything, because here I've also called our FV detector FV. So I accidentally named the variable the same way. And now that takes a couple of seconds longer, because we have a lot more simplices now that we need to allocate. And now we have a lot of chaos. Okay, something went wrong. What went wrong? That worked well yesterday. Oh. Some of the vertices are unfortunately very much outside the detector hull, so that's a bit of an issue. But that's not something that's actually that important, because most of the one problem we've encountered now with these with the isosurfaces is that since we're using a certain sample size of atoms in order to do our inverse reconstruction, some of the vertices might lie outside of the domain of our data set. And those vertices, they are then outside of any of the tetrahedra, and which means they don't have a meaningful barycentric coordinate. For anything that we actually want to do with the data, that doesn't matter all that much, because they're not inside the data domain anyway. And I can draw, I'll just make a sketch why with an isosurface you can have vertices that are happening outside. And switch back to the tablet. So essentially, when we're creating our voxelization, what we're doing is we're saying, okay, this is the atom prop data set, with all kinds of things in it, a couple of precipitates in our case. And what we are doing is we're essentially creating a grid. We're creating a grid and calculating what the concentration. Of course, our grid has to be fine enough to account for the small details in here. So this would be a much too large grid pitch. But what happens inside here is that we are calculating what the concentration each of those voxels are. And some of those voxels are partially inside the data set. That's why it's also very nice to know where the hull is. I haven't implemented anything that actually explicitly says, okay, that's the end of the data set, don't put any vertices there. Yeah, we can actually see that if we have a high value here, it might put one of the vertices of our isosurface that's, maybe I should draw one that's actually near the boundary. So maybe we have a data set here, maybe we have a precipitate here. So one of our vertices might be outside of here. But the tetrahedra that we've built, they are actually all inside per definition, because we took a sample of 100,000 atoms out of, in this case, about, I think, 20 million or whatever the data set size is, out of those 20 million atoms, and build a tetrahedra based on them. And sometimes we are going to be unlucky, and one of those vertices is going to be relatively far away from any of those vertices. And so we might run into numerical issues where the closest tetrahedron is somewhere, relatively far away and at a very shallow angle. And then this thing is just going to be projected somewhere, somewhere off into the distance. Practically, that's not actually too much of an issue because all of those vertices, they're not going to be the most important ones for your reconstruction. They're not going to be the super important ones for your reconstruction. But still, they are there. Of course, what you can do is you can go and have the hull, the dataset hull, clip the isosurface, so they remove any isosurface vertices that are outside the hull. This is something that is actually possible, but we haven't done that right now. And then same story as before. We can go and what is it called now? We can go and co-reconstruct again. So we can go and go. What did we call it? Object is an FV detector. And
you need to switch screens again.
Thank you. One of those days, I will remember how to do that. I will remember that will remember that I need to do that. Okay, and now we are going to co-reconstruct the objects. And barring numerical errors from something. It probably put some of the object vertices somewhere into infinity or somewhere very, very far away. Let's just have a look into that. So we can go and look into FV detector. FV detector, vertices. That all looks fine. The isosurface does have a lot of vertices. Okay, so what was the issue again? Integer logical values. Do we have the vertices? Okay, so maybe we have an error somewhere where we have a fractional, an index as a fractional bit. So FV detector, it was called FV detector. The third coordinates, we'll just need to round them in case we have some index that's sort of an index of, I don't know, 20,500.5, which obviously doesn't make sense because indices are full numbers. We'll just need to round that. Troubleshooting on the fly. Oh. You can see it's been a long day. FV detector, oh, FV detector dot vertices. Oh man. There we go. And now our objects should be reconstructible. Okay. So with 5 minutes left, I'm not going to chase the error there. But one thing that we can obviously do is we can split the objects. We can split. Sorry, where's the isosurface? So one thing we can do is just split the isosurface and just take, for example, that one precipitate that doesn't hit the surface. No, it doesn't hit the surface. Okay, do we have enough time for that? I don't think we will have enough time for that. Okay, so this was a bit of an introduction of how to do reconstruction with objects. Sorry, at the end it didn't quite work out as tested. It's always a bit harder when you're not as fast with moving stuff around an unfamiliar computer. But you've seen with simple things like a plane, you know, that's not a big deal. You can go and do an inverse reconstruction very easily. All you need is to have the coordinates in detector space and in reconstruction space. That's all we really need to have. So you need to have your EPOS file essentially, and then you can translate any object that you have created that doesn't do funky things like moving outside your data domain. You can reconstruct it back into the detector domain and then co-reconstruct it and then use that to drive your reconstruction. So today we were actually using some very, very simple objects, mainly the plane. But tomorrow we are going to learn how to make more complex objects. Tomorrow, not necessarily with the objective to drive a reconstruction, but tomorrow we're going to do that with the objective to do analysis. So we're going to do that with the objective to create analysis objects, and we're going to use those analysis objects to create proximity histograms, for example, from grain boundaries. We're going to use it to do local analysis. So we're going to look a little bit deeper into mesh objects and what we can do with mesh objects in outlining stuff. And then we're going to move to interfacial access measurements and interfacial access mapping finally. Okay, and with that, are there any questions? Probably also plenty of questions, and I'll copy the rest of the workflow into the chat as well, even the not so successful bits. No, that was wrong. No questions. Everyone's got enough for today already. Okay, if there are no more questions, then I will stop the recording and I'll see you again tomorrow at 9. And tomorrow we are gonna do the data analysis bit where we gonna look into how to do object creation and how to do advanced analysis of interfaces and the like. Yeah. So we're gonna expand it to n-dimensional analysis. Yeah. So it doesn't matter if you have a one-dimensional thing, if you have a zero-dimensional thing, or if you have a 15-dimensional thing. We are going to be able to analyze any of that.